Hello, everyone. I hope you're enjoying the summer school as much as I know I will be. When Emily asked me to record a short lesson on digital evolution, I thought, this is going to be easy. I've been doing this for a while. I've given overviews of this as part of talks before, but it turned out to be a real challenge for me. But it was a fun one. So here it goes. My 15-minute introduction to digital evolution. Before getting started, I think it's important to remember that the goal of science is to really try and make sense of our reality, which is this big, messy, organic mess, right? And we do that by trying to fit parts of it into boxes. And our boxes are never quite going to reflect the true complexity or a complete picture of reality, but by using different approaches and looking at different corners for hints, we end up with a better picture of what's going on as a whole. And artificial life, like any other field, is looking at things with a particular lens. And I will say that a defining feature of this community, though, is that the willingness to embrace sometimes strange or just outright wacky ideas. Uh, and doing so, I think, really expands the boundaries of the box that we happen to be looking within. And so instead of starting by reiterating what a life is, I figured I'd let the person who actually put this phrase on the books introduce it. So,
The field of artificial life is the attempt to capture biological phenomena such as self-reproduction, the origin of life, evolution, adaptation, growth, development, and differentiation in computers.
but I'm going to be talking about just one corner of artificial life, and that's digital evolution. And I'm going to start with the evolution bit, which can be summarized quickly, but don't let that lead you down the same path that I did and think that evolution is somehow sort of solved and easy and all figured out. That is absolutely not the case. And I spent a long time figuring that out for myself. But what it does mean is that evolution is a process, and we understand what the necessary ingredients are for it to occur. And those are adaptive evolution can occur if and only if there's reproduction, heritable traits, and variation in individuals' reproductive success driven by those traits. In other words, there's heritable variation that drives fitness differences. And if we have these three ingredients, then we can have evolution. And what this doesn't say is anything about DNA or RNA or the particular thing that is evolving, right? And that's an important insight and one that I think is sort of underlying much of the field of artificial life is that evolution is a substrate free process. It doesn't matter what's evolving, as long as it has these features, it can evolve. Now, for the digital part, I'm going to highlight some of the history that happens to run through my current institution, the University of Michigan. If you know who John von Neumann was, then you probably recognize his name as the inventor of the most widely used computer architecture, the stored program kind of method, sometimes called fetch, decode, execute, or the von Neumann model. But what you may not know is that he was working on building the sort of mathematical theoretical tools to describe self-replicating machines around the same time that he was working on the computer. And actually some of the first simulations that were being run on these very early computers were simulations of evolution. Now, one of the people that was working with John von Neumann was Arthur Burks, and he was recruited to University of Michigan to direct the logic of computer groups in 1956. And Burks had been working with von Neumann on this early computer, and Michigan wanted to sort of build their department, their expertise in this new emerging field of computers, right? And one of the first people that actually got a PhD in computer science was John Holland, and he was a graduate student with Arthur Burks. And John Holland really brought the fields of evolution and what was becoming computer science together. And one of his books, Adaptation in Natural and Artificial Systems, is really still a classic. And so are most of the books that John Holland wrote. I think they're just all fantastic and really deep dive into the theoretical notions of what adaptation means and how we can study not just sort of simple biological processes, but complex communities and ecosystems and social structures in digital systems. So he's definitely someone to be aware of. He also happened to train a lot of really fantastic luminaries in the field across lots of different fields, actually. So some that you may recognize: Stephanie Forrest. She's done a lot of work on these artificial immune systems, especially in sort of network security context, automatic programming and debugging, using evolution as a way of poking programs and seeing where they break. Melanie Mitchell, who's continued to be at the forefront of artificial intelligence and just kind of been an all-around complexity champion. And Eric Goodman, who's the previous director of the Beacon Center for the Study of Evolution in Action at Michigan State, was the first person to really take genetic algorithms, which were being developed as kind of this theoretical way of exploring evolution, way of kind of playing with toy problems in simulation, and apply them to real world problems when it would take, literal year to run these optimization processes on these computers that were, much slower than our current computers. And this is probably the only slide you'll ever see where Sparty, the mascot for Michigan State University, is on the same slide as the block M for the University of Michigan. But we still like Eric, so it's okay. And another one of Holland's student was Chris Langton. And we saw Chris just a few minutes ago introduce the field of artificial life. So he's definitely one of the forebears of this field. He sort of coined the phrase and held the first conference on artificial life. So the first artificial life edited volume, the first proceedings of artificial life here pictured, was published with Santa Fe Institute, and Langton was the sole editor of that. But he was interested in developing these self-replicating automata, much like von Neumann was. And so that thread of interest we can trace all the way back to the origins of computing to sort of the more modern creation of the artificial life field, right? In the realm of self-replicating computer programs, a lot of the early work can be traced back to Core War, which was itself influenced by proliferation of computer viruses in the early 80s. And Core War was kind of this game. It was an arena where different people would submit programs to compete against each other in this simulated array of memory. And the programs would have to compete for that memory, and the programs that sort of took all the resources of this computer, took more of the resources, would win. And what was really kind of cool and interesting was that pretty quickly it was realized that the programs that did this best were self-replicating programs. And this hardware had all of the necessary components to create self-replicating programs. And so those were the submissions to this competition that would win. And so this really kind of sparked the folks that were thinking about self-replicating machines and kind of evolution, and this led to sort of the next wave of, I think, digital evolution approaches. So the first one was Steen Rasmussen's attempts at building this kind of world where organisms could evolve and compete. And he took this core war idea, and instead of having these programs be submitted by humans, they would evolve, they would mutate. And so you would replace one instruction with another. And this was a cool endeavor, but it turned out that evolution was really not able to make programs that could adapt in this environment. So you would quickly see the degradation of just disarray, right? These programs would not be able to replicate themselves after just a few mutations would occur, and things just were very brittle. And this was actually the same problem that folks like Chris Langton was seeing in his self-replicating loops, von Neumann would see in his universal constructor mechanism. So these were core problems with the conceptualization of these early self-replicating systems. And it was really Tom Ray, a rainforest biologist by training, that had a solution to this problem. And he built a system called Tierra, where instead of having brittle computer code, he took inspiration from biology and used instructions that were built around things like pattern matching or structure, instead of arguments that were very brittle to mutations. So I'll let him talk a little bit more about Tierra.
When I created Tierra, I hoped to start the evolutionary process in a completely alien environment and let it diversify like organic life had. And I'd hoped to see something as rich as organic life, but I thought it would take years of tinkering to get anywhere close. Instead, what I found is that once I unleashed it in the computer, it took off on its own and diversified and became very rich without any further help from me.
After getting really excited by this work that Tom Ray had been doing, Chris Adami and this crew of folks here in the early 90s decided that they wanted to build their own system, and they wanted it to be a full-fledged platform to do research. This was going to be a scientific tool, one that could handle experimentation and manipulation in a way that Tierra maybe wasn't built for at the time. And so most of these people you might recognize now. They're in the same order in the left picture and the right picture. And really, this tool that they built, Avida, became probably the most successful digital evolution platform. And I'm going to spend just a second or two talking about Avita in particular. So I'm going to show you a little animation that Charles Ofria made about Avita. And so this is a circular genome of one of these digital organisms, and it's circular just in the sense that if you keep going around it, you'll end up looping back on itself. That's a useful feature in terms of not breaking a program when you're trying to allow mutations. These are the kind of instructions that the hardware can recognize, so they're sort of simple assembly-like instructions, and they're executed on a virtual CPU. And this virtual CPU has hardware that allows for things like input instructions, which will take values from the environment and store them in registers or stacks. Here I put it on the B register. Pop will take a value off of a stack and put it into a register. In this case, it's going to put it into the A register because that pop instruction was modified by the NOP A, or no operation. Add will add those two numbers together, and output will take the value that's in the C register, the output register, and output it to the environment. And this hardware also contains instructions that allow the virtual CPU to jump to different locations. It also has so there's control flow, right? So there's conditional branching. You have read and write heads that allow instructions to be read from one location of memory to another location of memory. And if you put all of those components together, you have all the necessary bits to create self-replicating computer programs that go through their genome one instruction at a time, creating copies of themselves. Now, it doesn't have to be the case that copy process is perfect every time. There could be random mutations introduced just by chance, and that introduces variation. And that, as you scale out to even bigger and bigger kind of zoom scales, you see these populations of different genotypes. Maybe most of these mutations are deleterious, but some of them will be beneficial. Some of them will lead to programs that are better able to copy themselves, to more quickly copy themselves. And those are the programs that are going to start spreading and taking over in the population, right? And so that has all the fundamental components of evolution, right? We have self-replicating, we have variation, we have heritable variation, and that variation is leading to differences in fitness. Now, these two self-replicating systems that were able to show how computer programs could actually evolve, they showed that evolution could occur not only when you had all of the necessary ingredients that we learned about in that Evolution 101 slide, but that there was this additional component that variation needed to be accessible by those mutations, that the system that was undergoing evolution itself had to be capable of evolving by random variation. And so this, to me, is a really fundamental insight about the nature of evolution as a process that was only really realized through these digital evolution systems. So to me, this is sort of like the basis of digital evolution. This is foundational knowledge about the world, right? But just like any other scientific field, right, we're just talking about one little corner. We're talking about digital evolution. And so I'm coming to this with a particular lens, and I've told you the history of one particular lineage through this field as it developed. There's lots of really cool other work going on. So I want to wrap it up with a definition. This is a general definition. What it means to be an instantiation of an evolutionary process is something that philosophers of biology have definitely discussed. I have opinions about, and so does probably everyone else in this summer school. So these are fun questions to ask about. And I'm going to end with just kind of a tour of a few different areas that I think are interesting and worth keeping your eyes on, and maybe some historical papers that are worth reading. So the first is thinking about these cellular automata systems. So you might have heard of cellular automata before. They're great tools for understanding complex systems, but they also found a home here in the artificial life world. And one thing that I think has been sort of kind of captivating recently is this system that Bert Chan developed called Lenia. It's beautiful. It sort of extends the classic game of life into more dimensions and creates these really organic looking organisms that can replicate and just do really cool stuff. So I highly recommend checking these videos out. Another person kind of in this lower level approach to digital evolution is David Hackley. And he's done fantastic work, has had a long career in this field, and definitely recommend checking out some of his stuff. But I think most recently, some of his work in Ulam, and this idea of generating very simple, robust first ways of thinking about living systems is going to be really powerful and interesting. So this is work that I would definitely check out. There's another system that, along with kind of Tierra and Avita, has been relatively successful in the field of having lots of groups pick it up and do experiments with it, and it's called AVOL. And this system is generally more geared towards understanding sort of existing biological systems, in the sense that it's taking the model of DNA and transcription translation networks and genes and their organization on chromosomes, and really digitizing that. So in some ways, this kind of pokes at the question of what it means to be an instantiation of evolution, or rather, I guess, what it means to be a instantiation of evolution in a digital medium, sort of that whole phrase, right? And if that doesn't mean anything to you, don't worry about it. These are kind of fun philosophical questions to get into. Of course, there's also this whole other area of science where people are using genetic algorithms, evolutionary computation. Maybe you heard some of this during the artificial intelligence section. But artificial life and these kind of digital evolution systems are clearly related to this field. And so this paper gives a good overview of the history and where these different approaches, kind of where they came together, where they diverged. And I'll end with this really fun paper that highlights how creative evolution can be. And there's even a YouTube video that shows a few examples of some of these surprising results that I highly recommend checking out. And I wanted to show this just because, well, not only because this is a really cool paper, but because the author list of this paper is a fantastic resource. These are all people that have done really interesting work in the field. And if you want to keep digging into digital evolution and this approach, check out these different people and see what they've done. I think this is a really, just the author list alone is a fantastic resource, but the paper is great as well. And I'm definitely happy to continue the conversation. Hopefully this gives you a good jumping off point for the field of digital evolution, and let me know if you have any questions.